on my buffer lab.
Where, the entire lab?
It's all good. I don't know where.
We'll talk. Okay, so I'm going to briefly go through this quiz. So here's the whole thing on 1 and 2. Okay? All that was happening on 1 and 2 was that you had an acid that was trying to turn into hydronium ions and anions. And if you're hardcore, you're going to put in the water and you're going to go, oh, that's technically hydronium ions and the anion. There's no titration. There's no base involved. There is no hydroxide, okay? I never said, hey, we're going to add hydroxide. Do not put hydroxide in here. It's not there. All this is trying to do is just ionize itself, okay? Now, here's the bigger picture. And you keep this in mind today when we talk about KSP, is that in this situation, your hydronium ions times your anions divided by the concentration of the acid is going to reach a specific value, okay? And that's what Mother Nature wants. So on number 1, both of these are starting off at 0. Oh, minus x, plus x, you all know the drill. The only thing that happens on problem number 2 is that now this becomes a buffered solution. So instead of that anion concentration starting at 0, now it's starting off at 0.1. So this is the mathematical part of it. This now instead of x becomes 0.1. That's a much higher concentration. So what I wanted you to explain on number 3 was the realization that, oh, it's the same Ka value because Mother Nature wants to be in equilibrium. But if you increase the concentration of your anions, what has to happen to the concentration of your hydronium ions? It has to go down, and there's an inverse relationship between pH and your hydronium ion concentration. So it's the same Ka value, and it's going to be the same story when we talk about KSP values. Anytime you have a value with a K in front of it, that means it's in equilibrium, and that's what Mother Nature wants to get to. So your anion concentration goes up, your hydronium ion concentration goes down, you get the same Ka value, pH goes up, okay? No hydroxides. Now, when you get to number 4, now we're going to add hydroxide to this. Oh, HA plus OH minus, you're going to get water and the anions. Now it changes. But again, you can work in millimoles, you can work in moles. I don't care. I worked in moles mainly because of the fact that I tell you, oh, we're going to add 0.02 moles to 1 liter. I was nice. I said, wow, let's just use 1 liter. Because then if you know what the molarity is, and if it's 1 liter, that's how many moles that you have. I didn't even make it complicated. It's like, oh, it's just the molarity is the same thing as the number of moles because it was 1 liter. So this is 0.02 moles. This is 0.02. That's 0. Minus 0.02, minus 0.02, plus 0.02. Boom. Once you get those numbers, then just all you're doing is plugging that into that Henderson-Hasselbeck equation. Okay, there's your anions. There is your acid concentration. Boom. That's all you got. All you have to do. When you get to 5, again, here's the only difference. Now, instead of that anion concentration starting at 0, now it starts at 0.1 because you have 1 liter of a 0.1 molar solution. But it's the same process. Minus 0.02, minus 0.02, bless you, plus 0.02. That's the only thing that changes is that this now becomes 0.1. Okay. On number 9, when you get to B. This is this complicated one because of the fact that your HA plus your OH yields your water and the anion. So in this one, you've got 20 millimoles of your base, you've got 20 millimoles of your acid, boom. This all goes away, 0, 0, plus 20. Now here's what I found odd, and I wrote this on some of your explanations on number 7, is that you did 9B right, but you missed question number 7 about which one's going to have the higher pH at the equivalence point. So if I wrote C9B, it's like you understood it mathematically, but you missed the conceptual part of it. So because this anion is going to react with the water, because it's the conjugate base off of a weak acid, you're going to start a secondary reaction that's going to reform the acid and hydroxides. Okay? This is the whole point of the story. Thank you.
What?
I'm so glad.
What was that thing they put? Female anthrax? Yeah.
It has a smiley face on it, you should
Oh,
smile.
there you go. It's for Joanna Spear, who I don't even have now.
I love Johanna.
Anyway, so here's what's going to happen here. Now you're starting this secondary reaction. And this is where you have to do the 2 steps. You have to find the KD by taking the auto-ionization of constant of water and dividing that by your Ka, which works out to be 7.7 times 10 to the negative 10th. Okay, so when you take the auto-ionization of constant divided by water, Ka, you get this. Now, because of the fact that this is not a titration problem, this is just an equilibrium problem, you have to have, and this plays out today with KSP and QSP, you have to have the molarity after they are mixed. So which means that you've got to take that 20 millimoles and divide it by the total volume, which is 300 milliliters, which gets you 0.0667. So when you do this, and you get KB equaling x squared over 0.0667, when you get x, you're finding your hydroxide ion concentration. Take the negative log of that, boom, there's your POH. C was the easiest problem on the exam, but some of you made it so god awful.
It wasn't me this time,
I
though.
apologize.
I didn't overcomplicate this one, Mr.
I
Brooker.
apologize.
Thank you. So if you look at
That's
what's
improvement.
happening on C, you've got 40 millimoles of hydroxide. You have 20 millimoles of your acid. Minus 20, minus 20. So I've got 20 millimoles of a very, very, very strong base, which is your hydroxide. Okay? Yes, are you going to start a little secondary reaction over here to make some hydroxides? Yes, that's like spitting in the ocean. Okay? Relative to this concentration from here. You have this excess base. All you had to do is take the 20 millimoles divided by the 500 milliliters. Your milliliters cancel out. You get a concentration of 0.04. That's the concentration of your hydroxides. Take the negative log of that. Boom, there you go. There's your POH. Yes.
I had 0.04 on there. I just used it wrong.
But like I said, Because this is what a lot of this test is going to be, okay? This is what a lot of this test is. That's why that's why there's another version of this quiz, okay? Because if you don't feel confident with this, you need to get to the point that you feel confident about this. Because this is what a lot of the test is going to be on,
How
okay?
much, like percentage wise?
50?
Like that.
Okay. Because there's only so much variation I can have on the theme. I mean, I can change the type of acid and the concentrations and the volumes. That's all I can really change.
Yeah.
You know,
Yeah.
the methodology stays the same.
So it's only gonna be like 2 pages?
Yes.
Oh no, it's like 3 pages front to back.
But like if it's it'll take up like this much though, right?
Oh yeah, I'll give you a bunch of space to write out, work the stuff out.
That's That's easy then.
Yeah.
Can I come in to request to retake quiz?
95.
Even if you want to
What
come
did
in
you
today
get?
to reflect and retake the quiz.
No, I heard what Bethany said.
Okay.
They both got B's.
Oh, okay.
Thank you for that.
They don't say B.
What?
I didn't explain one well enough, and I just messed up.
I got an excellent on one.
I still can't believe I didn't.
Lazy explaining.
But then when I did everything else, all the calculations. The one part where I made a polarity, I put 200. Pissed me off.
Here's like, I have a line for this.
I'm over this.
Okay.
No, you really got stuck in my
So, here's the last big concept that we have to cover. This is what's known as the solubility product concept. So, but here's the beauty of this. All we're gonna do is take the same ideas that we've already worked with and kind of repackage it into a different idea, okay? It's gonna be a little bit more complicated, but it's the same general idea. So let's start with this. What's the only time you put a K in front of anything? Then it equilibrium, okay? Now, so let me show you a simple demonstration. So I'm gonna take sodium hydroxide, and this is what I did on Wednesday. So I'm gonna take a little bit of sodium hydroxide. Is sodium hydroxide soluble or insoluble?
Soluble.
Soluble. All group ones are soluble. So what's gonna be important is that this is going to exist as sodium ions and hydroxide ions. And then to that, I'm gonna add magnesium nitrate, soluble or insoluble.
Soluble.
Why?
Nitrate.
All nitrates are soluble. You don't have to guess, all nitrates are soluble. Okay? I put some drops of that into there. We get a chunky white precipitate. Okay? Now, so the question being is that what's happened? How did we take 4 separate ions that were all soluble, 2 clear solutions that you can see through, that both look like water. You can't tell the difference looking at them. They have the exact same appearance. But yet, I mix them together and all of a sudden, I get a white precipitate. So what happened? So, if you look at the Chem 1 version of this reaction, okay, so let's start with the Chem 1 version. You have sodium hydroxide plus magnesium nitrate. Double displacement reaction, what do you get? You're a Chem 1 student, what do you get? You get magnesium, hydroxide, and sodium nitrate. Okay, woo, look at us, we're chemists, okay? And then I say, is it balanced? And you go, no, Mr. Burkamp, it's not. What do I need to balance it? Oh, let's put a 2 there. Let's put a 2 there, and it's balanced, and we're Chem 1, like, oh, yay for us, we just did chemistry, woo!
It's like a 5-year-old.
Okay?
That's a lot.
Now,
That was like us 2 years ago.
but then let's move to kind of the Chem 2 version of this, which is the net ionic equation. Oh, this is sodium ions, and that's hydroxide ions, and that's magnesium ions and nitrate ions, and then you have to decide which one of these could potentially be the precipitant. Could sodium nitrate be the precipitate, Graham?
Absolutely.
No, why?
Nitrate is always sodium.
And it's bonded to,
Sodium.
which is a group 1. You couldn't make sodium nitrate form a precipitate if your life depended on it. This is the poster child of solubility. What?
Cohen patted me on the back and I was suspicious of him.
I valid.
Yeah.
So what this means is that one of these form the precipitate and the sodium ions floating around in the nitrate. So those are like, these are your spectator ions. So the sodium ion is still a sodium ion over here. The nitrate ion is still a nitrate ion over there. So your net ionic is going to be Mg2 plus 2 hydroxides yielding MgOH2. Okay? As it is written.
Is that Chem 2?
That's the Chem 2. There's your net ionic. Boom, balance, right? Balance on charge, balance on number of
I'll figure it
particles.
out.
Chem 3.
Whatever we do.
Huh?
So now it's time for Chem 3.
Now there's just not even going to be an equation. It's
No,
just
there
gonna
is.
be
That's why I like the
alien
sign.
symbols.
It's scary.
No.
It's not even mine. I didn't make it.
Here's the shift that you have to make to understand KSP.
Jesus was both.
Here's the shift that you have to make. So, and you've heard me say this again, and I'll say it again and again and again. If you don't understand what is happening on the atomic level, you will never understand this concept, okay? So basically what happened is this. You had this precipitate of solid magnesium hydroxide. That is not the story. The story is not the precipitate, okay? It's not. The story is what's happening in the solution that's up above, okay? So what's happening is that this solution up here can only hold a certain number of ions, okay? That's it. It can only hold a certain number. If it exceeds that value, Mother Nature goes, I can't handle you as ions, you've got to sit down. It would be like me walking in here, my equilibrium number is 20. So there could be 20 of you up milling around, you're my students, I'm in equilibrium. Good, okay? Now, I walk in, and there's like 40 people milling around my room. Can't handle it, right? So what am I going to do? I can only handle 20 of you up walking around.
You're kicking people out.
I'm going to make some of you like, sit down, okay? I can't handle this situation. Because when I'm in equilibrium, I can only have a certain number of people where I feel comfortable up walking around. If you exceed that number, I'm going to flip out. Go sit down, okay? Especially if they're freshmen. Then I'm really going to flip out. So, the story here is not the precipitate. The story is up there in the ions. So, Mother Nature in any solution can only hold a certain number of ions. Now, here's what I want you to visualize. Imagine that you start off with pure water. None of this reaction is taking place. And I'm going to give you some magnesium hydroxide, solid magnesium hydroxide. And you're going to add that to this a little bit at a time. And you're going to mix it up, and you're going to mix it up, and it's going to dissolve. You won't see precipitate. So, if you look at what's happening, the magnesium hydroxide is trying to dissociate into magnesium ions and 2 hydroxide ions, okay? At some point, this water becomes saturated. It can't hold anymore. So at that point, if I add any more magnesium hydroxide to it, the water goes, I can't handle this, okay? I cannot accept any more ions. you have to stay as a precipitate. So once Mother Nature reaches that point, any additional magnesium hydroxide ions that you add cannot exist as ions. They have to stay as the solid precipitate. So if you look in your book on the back, this index, for example, if you look back here in the blue pages, you're going to find a whole chart of KSP values. Okay? So if you look up the KSP value for, it's on page 293, of magnesium hydroxide, so MgOH2 has a value of 1.8 times 10 to the negative 11, okay? So what that means is this. First off, if you look at all the Ka values, or the KSP values, if you look at all those KSP values, notice that they are all very small, and that's a similar thought process to Ka values. Oh, Ka values are really small because it doesn't ionize very much. KSP values are small because they don't ionize very much. It's the same idea. Now, so what we're saying is that if you look at this magnesium hydroxide, when this concentration of your magnesium ions multiplied by the concentration of your hydroxide ions, Mother Nature wants to reach this value, 1.8 times 10 to the negative 11. That's a very small number, okay? 1.8 times 10 to the negative 11. So since this is a very small number, when it reaches this equilibrium, what do you know about the concentration of those magnesium ions and those hydroxide ions? Really big, really small? Very, very tiny, because these numbers multiplied together have to equal 10 to the negative 11. So what that tells you is that Mother Nature can't hold very many magnesium ions and hydroxide ions. So there's a couple of things that you kind of have to, that get a little quirky in terms of this. First off, most of the time when we talk about like what's going to happen, we talk about the net ionic going this way to form magnesium hydroxide. So the net ionic is that you're making magnesium hydroxide.
You're so sweet.
But when you're talking about KSP, you're actually talking about that precipitate turning into magnesium ions and hydroxide ions. This is why this is important. So it's the same idea. Remember when we did Ka and we had the hydronium ion times the anion divided by the concentration of the acid, okay? Because that was HA turning into H plus and anions, okay? It was products over reactants. It was the product of your hydronium ions times your anions divided by the concentration of the acid. It's always products over reactants. The same thing is going to happen here. So our products are magnesium ions times my hydroxide ions. Now, where this gets a little quirky is that if there's a coefficient in front of the hydroxides, like there's a 2, that means that concentration gets squared. If there was a 3 in front of it, it would get cubed, okay? You didn't have to worry about that on the acid side of it because everything was just always in a 1-to-1 ratio. So where it gets a little bit something to think about is that this has the capacity to get squared or cubed. Rare that it ever goes to the 4th power. Okay? Rare that it ever goes. Second, third is even a little bit rare. But here's what you have to watch. If there's any coefficients, that has to get raised to that exponent. Okay? Now, if you look at this reaction, it's products over reactants. So this is why it's my magnesium ion concentration times my hydroxide ion concentration. Now, I need to divide it by the reactants, but here's the beauty of this. MgOH2 is a solid precipitate. We don't have to worry about it because the magnesium hydroxide is a solid. There is no concentration of the magnesium hydroxide because it's the solid chunky stuff down at the bottom. So the only thing you have to worry about is the concentration of the ions. I don't have to worry about the MgOH2, okay? It's there, but it's not it's not in the solution. It's just sitting there at the bottom of the beaker going, so, okay? What you focus on, and this is what I'm telling you, the story isn't the precipitate. The story is what's happening in the ions up above. That's what's determining this. So, what this means is that if you have that KSP of 1.8 times 10 to the negative 11th, what that means is your magnesium ion concentration times your hydroxide ion concentration squared is going to get you that number, okay? That's when Mother Nature is in equilibrium. So what that tells me, and it's the same idea, if I make my hydroxide ion concentration go up, what do you think is going to happen to my magnesium ion concentration? It's going to go
Down.
because you want the same, just like buffered solutions. If the anion concentration goes up, the hydronium ion concentration goes down because you want the same Ka value. So it's the same concept, okay? There's nothing new, we're just calling it something different, okay? That's it. Mother Nature wants to be in equilibrium. Now, where it gets a little bit complicated. And this is what we call QSP.
See, I understood everything until you gotta bring in the complicated stuff.
No, it's not that. So, when you have QSP, the only difference between KSP and QSP is that this is like a snapshot. Okay?
I'm gonna say Snapchat.
No, snapshot. Okay?
So you actually send streaks on
No.
QSP.
So, what this does is that it tells you the direction of the reaction. Now, here's what's of vital importance. Mathematically, it's the exact same. So if you talk about like the QSP of magnesium hydroxide, it's still the magnesium ion times the hydroxide ion concentration squared. It's the exact same, the formula is the exact same, okay? The only thing that changes is that this is the concentration right after the reaction is taking place, like right after you mix them together. So if I were to calculate the QSP for what I just did, I would have to have the concentration of my magnesium ions, and then I would multiply that by the concentration of my hydroxide ion concentrations squared right after they would mix. Now, oddly enough, we're going to do this just like you did. We're going to work in millimoles, then we're going to divide by the total volume to get molarity. So, let's start with something simple. So, I'm going to mix, so for example, what you guys are going to do in the lab. I might mix up together 4 milliliters of a 0.2 molar solution of magnesium nitrate, and then I'm going to mix up, you want to start with the easy one or the more difficult one?
Difficult?
Okay. Okay. So, this is what you're going to do. Like, you are going to measure out 4 milliliters of a 0.2 molar solution of magnesium nitrate. Okay? You're going to measure out in another test tube 6 milliliters of a 0.3 molar solution of sodium hydroxide. So imagine this. I've got 2 different test tubes. Boom. We're dumping together. Okay? The exact sound it would make. Okay? So when I mix them together, so I'm going to put these together inside a beaker. Now, right away, let's start with the obvious. What's the total volume going to be?
10 milliliters.
So I know my total volume is going to be 10 milliliters. But I need the concentration after they've been mixed. Now, if I start with 0.2 molar solution of magnesium nitrate and I increase the volume to 10 milliliters, what's going to happen to the concentration of my magnesium ions? It's going to go down because I'm going to put it in more volume. The same thing is going to happen to the concentration of my sodium hydroxide. It's going to go down because I have more volume. So I have to have the concentration right after they're mixed. So here's the easiest thing to do. So this is technically going to exist as magnesium ions and nitrate ions. If I'm going to calculate QSP, do I worry about the concentration of my nitrate ions? No, not part of the story. Don't care. Are they there? Yes. Do I worry about them? No, they're not part of the story. Do I worry about the concentration of my sodium ions? Nope. Are they there? Yep. Do I care? No.
That's kind of neat.
I'm just telling you. Okay?
Your feelings.
Now,
Important. We should do something with those.
so
Crying right now.
what you're looking at is magnesium hydroxide turning into magnesium ions and 2 hydroxides. Okay? That's what's going to generate these ions after I mix them together. Okay? So, good for you.
It was tucked in the very front of the chemistry book.
Weird.
That's a crazy place to put it.
Weird. And it was due when?
Like, okay, I could have told you yesterday, but you wouldn't have even seen it. You weren't here.
I came back after school. How do you think I got the quizzes?
Magic.
Oh, I assumed like you got just teleported.
Magic.
You live here though.
It's crazy.
Okay.
The hidden
Now,
was-
you can do this, oddly enough, with a rice chart.
It was
Get out!
I love rice.
What do you think the initial concentration of the magnesium ions is when you go to mix it? 0? Okay? Non-buffered solution, it's just 0. Now,
0.
here's the story.
AP chemistry is just.
If I take 4 milliliters and multiply that by 0.2, what am I going to get?
0.8.
0.8
Yes. Millimoles.
0.8
millimoles.
millimoles of my magnesium. That was. I can't write. I can't.
8 millimoles of my magnesium.
Millimoles.
Millimoles of my magnesium. That's tough to say. Millimoles of magnesium ions.
Well, I think you said it perfectly this time. Millimoles of my magnesium.
If I take 6 times 0.3, I get 1.8 millimoles of my. True?
Yes.
But do I need millimoles to put into this equation? No, they're square brackets. What do I need? Molarity. So what am I going to divide by? Oh, divide by the total volume. So I'm going to divide both of these by 10 milliliters. Why?
Because
Add them together.
Yes, the
Plus
total
4.
volume now is going to be,
This many plus this.
right?
This many.
So if I take 0.8 and divide that by 10, I get
I did it with other cousins.
0.08. If I take 1.8 and divide that by 10, I get,
0.18.
so this becomes 0.08, this becomes 0.18. What's happened to the molarity after I've mixed them together? It's decreased because I have the same number of ions in more Solution, so the concentration goes down. Now, at this point, Mother Nature's going, how are we going to play this? Now we're going to calculate the QSP. So the QSP is the snapshot right after it was mixed. Okay? Right after it was mixed. So that's going to be my magnesium ion concentration, which is going to be 0.08. Do I have to square or cube or anything with that?
No.
No, because it's just straight magnesium. My hydroxide ion concentration is going to be 0.18, but that's got to get squared. So somebody take 0.18 times 0.08.
It makes sense.
What are we getting?
Just chill out. So somebody take 0.18 squared times 0.08.
2.59 times 10 to the negative third.
2.59 times 10 to the negative third.
Yes.
Now, at this point, Mother Nature has to decide, am I cool with this or is this bad? So, at equilibrium, the KSP value is whatever that is. It's a really, really small number. 1.8 times 10 to the negative 11.
Me too, man.
So, Mother Nature goes, when I multiply the magnesium ion concentration times the hydroxide ion concentration, I want this number. But what do you notice about the QSP value?
Very big.
It's very, very big. So Mother Nature at this point goes, this is bad. Okay? So what's Mother Nature going, what's the only thing Mother Nature could do?
Make some sit down.
Yes, so Mother Nature's going to walk in and go, wow, this is bad. There's a whole bunch of freshmen in my room. Y'all sit down right now. Okay? Boom. Okay? Sit. So at this point, Mother Nature is going to make a precipitate because the QSP is much, much, much bigger than the K. It is a
Four
lot.
muches.
Hey, that's at that point that's an arrow, and we don't do arrows. That's too many.
It's a lot. So here's the general rule. If your QSP is bigger than your KSP by about a factor of 1,000, you're probably going to get, that's when you're going to get a visible precipitate. Okay?
Excellent.
Now, so Mother Nature goes, this number is too big. I can't handle it. The only alternative that can happen is to do what? Make it precipitate. So this is what happens. Mother Nature goes, hey, y'all need to simmer, okay? And just take a seat. Okay? Oh, or have you thought about just chilling out? So,
That was crazy.
I know. So at this point, Mother Nature
Mother
goes,
Nature's my therapist.
so I'm telling you. Life coach, Stanford Camp, life coach.
You should start that.
Oh no!
And then you
Oh
put
no!
racing
I would
through.
make people cry. It's like, suck it up.
Chilling out.
Yeah.
I think people can
I
use
get
that
that.
better.
Okay. So do you see what's happening? So the QSP was too big. Mother Nature goes, I got to drop this concentration down so that I can be in equilibrium. The only thing Mother Nature can do is do what?
Two.
Better.
See?
I miss Mr.
I miss
Johnson
him every day.
Okay.
Better.
Now, that was the complicated one. Now let's deal with the simpler one. So let's say that I had 5 milliliters of, whatever that was,
Brainwashing the smart kids. No.
a 0.2 molar solution of my magnesium, and I'm going to mix that with 5 milliliters of a 0.3 molar solution of sodium hydroxide. Okay? Now, this is why this is simpler.
Let me tickle you.
What are you going to do to the volume? Mathematically. By how much? Or double it, right? So if I have the same concentration in twice the volume, what's going to happen to the molarity? It's going to be half as much. If you don't believe me,
You go over the math again.
take 5 times 0.2. If you take 5 times 0.2, you get,
Math doesn't.
What?
well, you get 1 millimole, true? And if I take 5 times 0.3, I get 1.5 millimoles, true?
What am I feeling?
But what's your next step? To divide by what?
10.
The total volume.
He'd say math does
I didn't
not
lie
lie.
and then realized like.
I'm gonna divide by 10 millimoles.
Whoa, that's pretty.
Guess what? This becomes,
0.1.
and this becomes,
0.15.
In math, you have
That's
to
crazy.
prove
So
that
good
you're
at that.
wrong.
I've gotten so good at mental math.
I don't know why
Okay.
it's funny.
now, so here's, now, would it have made any difference if this had been 20 and 20?
No.
No. So as long as you add equal volumes, the concentration just becomes
Half.
half as much. Okay?
Why
Excellent.
didn't we start with that?
And this is why in the lab, okay, which we're gonna do on Monday, you're gonna add 4 milliliters of each one. So, once you add the 4 milliliters of each one, what's gonna happen to the new concentration? It's going to be half as much, okay? So that's why I said the easier one is if you just have equal volumes, okay? Then you just take the concentration and divide it by half, okay? All right, Kevin, stop you on the camera. What I'm gonna hand out next is not your assignment,